Hi, today we're going to talk about atmospheres and why they're different. Why do you find some things in an atmosphere and not others? So let's start out by talking about three very different planets. Mars is what we call a rocky planet. Earth is also considered a rocky planet, but it's very different from Mars because it has lots of liquid water and it has a fairly thick atmosphere. Jupiter is what we call a gas giant. But what does that even mean? And why are all of these planets so different? So earlier you watched a video on differentiation, which is basically a separation based on density. The denser materials sink to the core of the planet, while the less dense ones rise to the surface. And that, for example, is why the core of the Earth is made of iron, nickel, and other heavy metals, while the layer closest to outer space is composed of gases. Now let's look at a cutaway of the planet Jupiter, which is a gas giant. As you can see, the outermost layer is in fact made of gas, in particular hydrogen. But once you get down a few hundred miles, that hydrogen becomes a liquid because of the great pressure. At the very core of Jupiter, there's a much denser mass which might be made of rock or ice. In other words, Jupiter may also be made of rock and metal surrounded by gas, just like Earth. But Jupiter's surrounded by a different gas. So why does Jupiter have an atmosphere of hydrogen? Well, the Earth has a completely different atmosphere composed of nitrogen, oxygen, etc. The answer lies in something we call escape velocity, which is basically the minimum speed an object needs to move in order to escape from the gravity of a massive body. Now, of course, in this case, that massive body is a planet and its gravitational influence. So here's the equation for escape velocity, and let's talk through what all of these variables mean. This is our symbol for escape velocity, and that's equal to the square root of 2 times, first, the gravitational constant, times the mass of our massive body, which of course is our planet, and then all that divided by the distance between the object that's trying to escape and the center of gravity of, in this case, the planet. Now, this is really important. The escape velocity for an object sitting on the surface of the Earth is going to be different from an object that's in a 100-mile high orbit. So now let's take a look at an example of escape velocity. Let's say we want to have a rocket take off from Mars, perhaps as part of a sample return mission. So we aren't actually going to calculate the escape velocity of Mars in meters per second, but instead we're going to calculate it relative to the escape velocity of Earth. So Mars has a radius that's just about half of Earth's, and so people often say it's half the size of Earth, but the mass of Mars is only 1/10 that of Earth. So there's less mass to escape from, but on the surface, you're also closer to the center of gravity. Now, if you do the math, you'll see that the escape velocity of Mars is about 43% that of Earth. Now, why are we talking about escape velocity in regards to atmospheres? Most people, when they hear that term, think of a rocket or something like that escaping Earth's gravity. But escape velocity is also applicable to molecules of gas in the atmosphere. If a gas molecule is traveling quickly enough, it can escape a planet's atmosphere and fly off into space. So let's talk a bit about temperature and kinetic energy and how they relate to velocity. Remember from Gen Chem that temperature is a measure of the average kinetic energy of a system. So the higher the temperature, the higher the kinetic energy you're going to have in that system. And now let's look at the equation for kinetic energy. Kinetic energy is equal to 1/2 times mass times velocity squared. Now, just because you have an average kinetic energy at a given temperature, that does not mean that all the molecules in the system have the same kinetic energy. It's the average kinetic energy, right? So it's actually more like a Gaussian curve. And for a particular temperature, that Gaussian curve of energies translates into a range of velocities as well. And for any given system, there will be a fraction of the molecules whose velocity is equal to or higher than the escape velocity. But what if you increase the temperature in the system? You're going to have a different Gaussian curve of velocities, one that has a higher average velocity. And the fraction of molecules equal to or above the escape velocity will be higher. So the higher your temperature, the more likely you are to lose molecules from your atmosphere. Now let's look at one more facet of kinetic energy, which is the relationship to mass. You see, even though two particles have the same kinetic energy, if they have different masses, they will have different velocities. And so if we think about this graph not as two curves relating to two different temperatures, but rather as two different types of gas molecules at the same temperature, we will see that the lighter gas, helium in this particular example, will have a higher fraction of molecules above escape velocity. This is very important in Earth's atmosphere. Radioactive decay processes produce both helium and argon, but since helium can escape Earth's gravity more easily, our atmosphere is relatively deficient in helium. By contrast, argon is massive enough that it tends to be retained in the atmosphere, which is why Earth's atmosphere has a relatively high argon content. All right, there is one more factor in whether a planet can hold onto an atmosphere or not, and that is whether or not it has a magnetosphere. We call Earth's magnetic field the Van Allen belts. Now, the reason magnetic fields are so important is that the sun is constantly spewing a stream of charged particles, primarily protons and electrons. So this is what we call the solar wind. If these particles impact the upper atmosphere, they can do two things. The first is to cause nuclear reactions. In fact, this is how we get the formation of carbon-14 on Earth. But the other thing they can do is to impact a molecule and pass on extra kinetic energy that then allows that gas molecule to reach escape velocity. So in other words, they create better conditions for molecules to escape the atmosphere. So luckily for us, the Van Allen belts redirect these charged particles away from Earth. If our planet did not have a magnetic field, we would have a much thinner atmosphere. So there are a lot of factors that contribute to whether or not a planet has an atmosphere. And if it does have an atmosphere, what sort of atmosphere it has. The larger the planet, the higher its escape velocity and the more likely it is to retain gas molecules. The higher the temperature, the higher the average kinetic energy of atmospheric particles, and the more likely it is that atmospheric particles can escape. Atmospheres made up of higher molecular mass particles are more likely to be retained. And of course, magnetospheres help keep an atmosphere from being affected by the solar wind. In a sense, we are lucky here on Earth. The temperature is not too high, our planet is moderately massive, and we have a fairly strong magnetic field. But not all planets are so lucky. So we're going to talk about other planets' atmospheres in class. I hope this was helpful, and I look forward to seeing you again soon.